34.3. Okay, we're going to talk about standard FOB change of neutralization today. So last videos we talked about the standard FOB change of combustion. Remember the definition composed of 3 parts. Okay, this have 1 mark on this. Okay, remember FOB change when 1 mole of substance is burned in oxygen under standard condition. Okay, don't miss any part. And the target where the fuel or the substance to be burned have to be 1 all the time, and the reaction must be negative. So next standard FOB change of things, okay, the reactions that we're going to talk about, that will be neutralization. So you can see that neutralization, we use an N to represent. If you remember neutralization, it must be talking about acid plus base. Okay, acid plus base. Okay, so you may have many different kind of neutralization. For example, you have HNO3 react with the NaOH, okay, and then you give salt and water. So in the process, you can see that it will be also be negative. Okay, it have to be negative. Remember, neutralization is also a exothermic reaction, so all the time it will be negative. But when we write an ion equation, it will be easier for us to see that. Okay, actually, the reaction happening is H plus combined with a hydroxide ion. Okay, it's a bond forming reactions, and then it release energy. Okay, so basically most of the time you will find that the neutralizations FOB change of neutralization equals to negative 57.3, but in general it will be negative. Okay, so your target is to memorize the definition. Again, okay, it will have composed of 3 parts. The first part, what is that? That is a FOB change. Second one, when 1 mole of the target we talk about this time, because we can have many different kind of acid and alkaline. So the target, okay, for this reaction must be water. Water is the target in neutralization. When 1 mole of water is produced from neutralization between acid and alkaline, that will be the second statement. Okay, important point for the definition. Last one, okay, because this is also a standard reaction, so therefore you have a standard FOB change of reaction. So basically, okay, the definition is composed of 3 parts, and then you have to remember the definition of this. Okay, so that will be the second part. Third part, that will be the features. Okay, remember just how we mentioned, okay, the coefficient must be 1. This time the target is water. Okay, this time the target is water. So therefore, water must be 1. Okay, and also it have to be negative because it is an exothermic reaction. That will be the key features of neutralization. Okay, so we can have a look a little bit more examples here. So like HCl, NaOH, they form NaCl and H2O. When we write this, okay, remember H2O have to be 1. This one will be all right. So you see that this one is a dibasic acid. Okay, basically when you do the balancing, we have used 2 NaOH and then Na2SO4 and 2H2O to show that. But remember, this one, okay, is about the standard FOB change of neutralization. So all the time, the H2O have to be 1. Okay, so in this case, so you see that you have you have 1 H2O, and this one also have 1 H2O. So balancing, okay, you have to pay attention to that only. Okay, so these two, okay, these two examples, okay, we're having strong acid, strong alkaline, strong alkaline. So you'll see will be negative 57.3. Is it a must for every kind of neutralization? Let's have a look. So, is it E always equals to negative 57.3? You can check it right here. Answer is not. Okay, some of the reaction you will find that the acid and alkaline, when you change it, okay, you may have less negative, okay, in the process. But in general, you'll find that, okay, for these 5 pairs of acid and alkaline, why it will be less negative? Because you can easily identify some weak acid and weak alkaline in it. Okay, if you're using the strong one like HNO3, HSO4, all of these are the strong alkaline. Is that right? Strong acid and alkaline. So this one, we're talking about the strong acid or alkaline. While the yellow one, we're referring to the weak acid or alkali. Okay, so whenever the neutralization you involve a weak acid or weak alkaline, then you realize that the energy release will be less than 57.3. Okay, so you can have a look of the equation on the left hand side. When you have like HCl and NH3, NH3 is a weak alkaline. Is that right? Just as we mentioned, NH3 is a weak alkaline. So therefore, the energy release will be less. Less negative means release less energy. So where some of the energy go? Okay, so this one HCN is also weak acid. Okay, hydrocyanic acid. Okay, you haven't seen that before. Okay, but that will be a weak acid as well. Okay, so you will find that some energy have been used. Okay, in some area. Okay, where have the energy used? Okay, if you remember weak acid. The definition of weak acid is it is an acid which partially ionized in water to give hydrogen ion. Okay, so the key points of weak acid is it is partially ionized in water. Okay, partially ionized in water, that means not 100% of the molecule will be ionized to give H plus. If we imagine we have like HCN, okay, we got 2 HCN right here. HCN here. One of them, they will form ion. While the other one, it will just like a molecule here. Okay, it will like a molecule here. When you have like NaOH, for example, we got 2 OH minus ready for doing the neutralization. The first one will be quickly to combine with the H plus which have been ionized. But the second one, this one have to be waiting because this molecule not yet ionized. To break this bond, extra energy need to be absorbed to ionize this. That means in the process you have to overcome this bonding. Then the H plus will then combine with this OH minus. So some extra energy have to be used to overcome or to ionize this molecule first. Okay. So when you're asked why this one will be less negative, when like neutralization between a weak acid and strong alkaline, then you may say that because in the process some energy is used to completely ionize the weak acid and alkaline. So in the process, we have less energy release. You may say less energy release, or you may say that the reaction is less exothermic. Or you will say that less negative in the value. Okay, but remember, never say that the standard enthalpy change becomes smaller, because smaller, this word is so ambiguous. Okay, you mean smaller in value, that means more negative. Okay, this one, when you say that it is becomes smaller, normally because of the ambiguity of these terms, normally you won't score any mark. Remember, in this exothermic reaction, whenever you say that less energy release, you have to say less negative in value. So this will be the key parts of the standard enthalpy change of neutralization. If it is including weak acid, energy is used to completely ionize a weak acid. So therefore the whole reaction will be less negative, less energy release in the process. Get it? So let's have a look of some exercise. So class spread 34.2. I'm not going to do all of them with you. Just focus on methane. Maybe one of them. For the rest, like the butane and also hydrogen, please do this on your own. So for methane, first of all, write a chemical equation for the combustion of each fuel. Chemical equation. We are not writing thermochemical equation, so just balance the equation will do. So we have like methane. We have with the combustion, you need to burn in oxygen, and you like have CO2 and also H2O with 2 H2O here. So in total on the right hand side we have like 4 O. So you have 2 O2 here. So this first part will be like that. And then based on the information in table 34.1, on page 7, I've put it down here for you. Calculate the heat release during combustion of 1 gram of each of them. So now you are given 1 gram of methane. So you're going to find out how much energy will be released in the process. First of all, you have to convert the gram into mole first. So therefore, the number of mole of CH4 we have will be 1 over 12 plus 1 times 4. So this will be equals to 0.0 625 mole. Okay, and then let's have a look of the enthalpy change of combustion. Okay, this one is per mole. Okay, so we'll find that each mole it will release 890.4. So energy release, because I have the word release here. Okay, so we're talking about the negative sign. Okay, you have the concept of negative sign here. So if you say energy release, okay, then you may just use 0.0625 times 890.4. You see that I didn't use negative here because I use energy release. Okay, I say that it is a releasing energy. That means it's negative already. So if you do like that way, then you can find that it will release like 55.65 kilojoule. Okay, so all the calculation will be like that. Okay, you can use the same method to do butane and hydrogen. Okay, and then you're going to find out which one is the best fuel. Okay, if you compare each of them, they're using 1 gram. The one release the most energy. Okay, that should be the best fuels. Okay, for the rocket fuel. Okay, so that would be like that. Second question, okay, this one is a very important exercise, okay, so do remember, put star for this one, question number 2. So, standard enthalpy change of neutralization, we know that, okay, in general, that will be negative 57.3, we're expecting this, okay, maybe 57.3 or 57.2 or whatever it is, okay, but whenever we have weak acid or weak alkaline, we'll find that will be less negative. So have a look of the first question. Using above data, answer the following question, which is the weakest acid. Okay, so we got our weak acid here. Okay, we got some weak acid here. So we are using same alkaline. This is weak acid, and we will have like some weak alkaline here as well. So we will find that 1, 2, 3, 4 of them. Okay, they're having a releasing less energy, less than 57.3. So we'll expect that one of them, okay, must be a weak acid or weak alkaline. So because we have like all these are the NaOH, okay, so only the acid change. So we see that, okay, among this, okay, this will be released the least energy comparing to this one and this one, right? So therefore we'll know that this one, okay, they need more energy to do what? To completely ionize this acid. So we'll say the weakest acid, that means least ionized. That would be the weakest acid. So among all these, okay, we can tell the first one will be CH3, CH2, COOH. That means ethanoic acid. Okay, then now we have a look of the weakest alkaline. Okay, so we have like NH3 and also CH3NH2. So this one, okay, will release less energy comparing to this one, right? So therefore, the weakest alkaline, it should be NH3 because you need more energy to completely ionize. Okay, so these two, basically we compare the data like this. And the most important part, go to part C. We have to estimate the standard enthalpy change of neutralization between the weakest acid and weakest alkaline. That means right now, okay, we try to put these two together. This one and also NH3. When they react, what should be the standard enthalpy change of neutralization? Okay, quite interesting, okay? So first of all, we have to calculate the enthalpy, okay, are required to completely ionize this one first, and also we have to completely ionize this one. Okay, we have to calculate this, okay? So first part, okay, it will be this one. How much we have to ionize ethanoic acid? We are going to compare these two values because this one is a standard enthalpy change of neutralization. And then this one, okay, we will know that some energy have been used to neutralize, to ionize the ethanoic acid. So we're going to find this out. So it should be a positive value. So energy required to completely ionize the CH3, CH2, or COOH. Oh, this one is propanoic acid. Sorry, I just making a mistake. Propanoic acid. So this one, okay, will be 49.9. We're going to minus negative 57.3. Okay, by doing this, okay, we find that we have used 7.4 kilojoule per mole to ionize the propanoic acid completely. We use the same method. Okay, we can do the subtraction like 52.2 minus 57.3. By doing this, okay, we will know that, okay, we need 5.1 kilojoule to completely ionize it. Okay, so lastly, okay, the standard enthalpy change, what will that equals to? This one will then be equals to 57.3 plus 7.4 plus 5.1. This one is the energy absorbed to ionize propanoic acid and also ammonia. So by solving this, then you will find that most likely that will be only releasing 44.8 kilojoule per mole. Okay, so this one is a very interesting example. So I highly recommend you to tag it in your book, okay, and then redo it for a few times. Okay, so to summarize these two videos, first of all, for the definitions, okay, remember, standard enthalpy change of combustion is the enthalpy change when one mole of substance is burned in oxygen. And then all of them, okay, they should have like under standard condition. Okay, so for the feature of combustion, okay, remember the substance to be burned must be one all the time. Okay, and also combustion is exothermic for sure, so it must be negative. If you calculate something positive, that must be wrong. Okay, and then now goes to neutralization. It's an enthalpy change when one mole, the target is talking about water, is produced from neutralization between acid and alkaline. Every single word, okay, please include it in your definition. So the target will be water, so therefore remember the feature of it, coefficient of water must be 1. Okay, and also it must be negative as well. Most of the time, okay, will be negative 57.3 if it is a strong acid, strong alkaline. Okay, strong acid, strong alkaline, strong base. Okay, so you'll find that it will be negative 50.3. But if you have a weak base with you or weak acid with you, then at that time you'll find that, okay, some energy is used to completely ionize the weak acid or the weak alkaline. So therefore it will be less negative, okay, to comparing to the negative 57.3. So that's all for this video. Bye bye.